All right, today we're going to talk about variation of parameters. So the last lesson we did was the method of undetermined coefficients. And it's fabulous, except that it only works on special cases. So first of all, your L has to be all constant coefficients, can't be any functions, and F had to be a certain type. And I listed out those types in that last lesson on 5.7. Variation of parameters has less restrictions. L doesn't need to have constant coefficients, and the only restriction on F is continuity. So here's the idea. The idea, what we're going to do today, is if U1 through if U1 through UN are linearly independent homogeneous solutions to L operating on Y is equal to 0, then we're going to let the particular solution be some function on X times U1 plus some function on X times U2 all the way through some function on X times UN for the non-homogeneous differential equation L operating on Y is equal to F. And the result, and this is for the case when n equals 2, is if U1 and U2 are independent homogeneous solutions, to L operating on Y is equal to 0, then the particular solution, C1 of X, so that's some function of X times U1 plus some other function of X times U2 satisfies the non-homogeneous differential equation L operating on Y equals F when two equations are true. That C1, now truly, let me show you the, okay. Keep in mind, C1 is a function of X. It's not a constant, right? So C1 is a function of X. If you take the derivative of it and times U1 plus the derivative of the second function times U2 is equal to 0. And if the derivative of the function on X times the derivative of U1 plus the derivative of C2 times the derivative of U2 is equal to F divided by A naught, where A naught is just your leading coefficient. All right, so we've got the particular equation is going to be some function of X times U1 plus some other function of X times U2, and these two equations have to be satisfied. This is just A naught that is the leading coefficient. All right, those are the two things that we're going to end up using, and let's do it. So first example is y double prime minus 2y prime plus y equals e to the x over x. And so that's your F, right? And I'm going to rewrite the left-hand side as this is d squared minus 2d plus 1 operating on y is equal to e to the x over x. By the way, e to the x over x is continuous over its domain. It's continuous except where x equals 0, but x is 0 isn't in its domain, and so it's considered a continuous function because it is continuous over its domain. All right, so we do have constant coefficients, right, for L, but F was not one of those special types that we could use the method of undetermined coefficients on. So we start by doing what we do, right, to change this to d squared. That factors, that's a d minus 1 quantity squared of y is equal to e to the x over x. And here your r is 1, but it's got a multiplicity of 2. And so we're going to write we're going to get the homogeneous solutions to if this left-hand side had been set equal to 0, then the homogeneous solution would be some constant times e to the 1x plus some other constant times x times e to the x. That's just a real root with a multiplicity of 2. All right, so then what we're going to do is say, okay, these guys, definitely independent, homogeneous. This is a homogeneous solution, right? And so now we're going to let the particular be some function of x times u1, so times e to the x. So write it like that, yeah. And then plus c2 of x, right? Some function of x, and then times x times e to the x. Yeah. So this is some function of x, and this is some function of x. Keep in mind, those are not, it's not c1 times x, right? This is some function of x, and this is some other function of x. It's not a constant times x, so be careful on that. And in fact, what I'm going to do is I'm going to drop off. That's the reason why up here when I listed it, I didn't do c1 prime of x because it just gets confusing. So I am going to drop off the functions of x just so that there's not a bunch of crazy writing that I will end up thinking is a multiplication happening when it's not. Okay, so that means that I'm letting this guy be my particular. Now, it is the particular as long as it satisfies those two equations. So we have that c1, the derivative of this function of x times e to the x, plus the derivative of c2 times x times e to the x must equal 0. That's that first equation that it must satisfy. And the other one is that the derivative of c1 times the derivative of e to the x. So u1 is e to the x. Derivative of e to the x is still e to the x. All right. And then plus the derivative of c2 times the derivative of x times e to the x. And so that would be derivative of x is 1, so a 1 times e to the x plus x times the derivative of e to the x, which is e to the x. And this is going to equal e to the x, f, right, e to the x over x, divided by its leading coefficient, which was a 1. So there we go. These are the two equations that it must satisfy. So what I'm going to do now is we need to solve these two equations. Two equations, two unknowns. My unknowns are the c1 prime and c2 prime. Those are my unknowns that I need to solve for. And so I'm going to use linear combination method, right, where if I just do the second equation minus the first equation, then these first two terms will cancel out. So I'm going to take these guys and I'm going to subtract the second equation minus the first equation. And that will give me, these two guys cancel out. I would have a C2 prime times, this is an e to the x plus x times e to the x, and then minus x times e to the x, and then equals e to the x over x minus 0. So that was just subtracting, I took the second equation and subtracted the first one from it. And if you notice, bye-bye, bye-bye, bye-bye. All right, so that means that you've got C2 prime times e to the x, and so I'll divide both sides by e to the x, and I get C2 prime is equal to 1 over x. Plug that into the first equation to solve for C1. You could plug it into either, but definitely the first one's the easiest. And I would have C1 prime times e to the x plus 1 over x times e to the x equals 0, which means that, oh, nice, those guys cancel. And you'll have a C1 prime times e to the x plus e to the x. So if I subtract it, I'd have a negative e to the x. And dividing both sides by e to the x gives me that the derivative of C1 is negative 1. Okay, so I know the derivatives. I need to find what these functions are, right? I need to figure out what is C1 and what is C2. But we can just find the antiderivatives of these guys. So C1, remember, it is a function of x. I'm going to add that back in now because now it doesn't look so confusing. But C1 is some function of x, and you get it by taking the antiderivative of this guy by integrating negative 1 with respect to x. Yeah? And that's just negative x. And do the same thing with C2 is some function of x, and you get it by integrating 1 over x with respect to x. And we know that that is the natural log of the absolute value of x. So that means that my particular is, can I get it all on the same screen? Nope, but we're going to take the function that we just solved for, C1 of x. We're going to go negative x times e to the x, and then plus the function we just found for C2. C2 of x is the natural log of the absolute value of x. I'm going to plug that into that, times x times e to the x, and that'll give me my particular. So I've got that the particular equation is negative x times e to the x plus the natural log of the absolute value of x, and then times x times e to the x. And you know, of course, I'm going to make sure my shirt is on the right side out and put that in front because that bugs me. Oof, it looks ugly. Does not look right. All right, so then what's your solution? Well, your general solution is the homogeneous part, which was C1 e to the x plus C2 x times e to the x. So that part was from the homogeneous solution, YH. And then we're going to add to it the particular, which is this guy, and that was minus x times e to the x. And then, like I said, I'm going to put this in front of the natural log because it just does not look right without that. There we go. And here is the particular solution. There's your answer. Not that you have to label your homogeneous and particulars. I'm just making it very clear how I'm getting where I'm getting these functions from. All right. Not too shabby, right? Let's do another one. There just for a minute. Okay. Let's do example 2. is we're going to solve the differential equation y double prime plus y equals secant of x. Okay, now if I rewrite this left-hand side, that is d squared plus 1 operating on y is equal to secant of x. Solving this guy, that means your r would be plus or minus I. So you got complex roots but no multiplicity. But your a is 0 and your b is 1, right? Because those are both 0 plus or minus I. So a is 0, b is 1, which means your homogeneous solution would be C1 times e to the 0 cosine, well, 0x, and then times cosine of b times x, so it's just a 1x, plus C2 e to the 0x times sine of 1 times x, which of course that simplifies. So my homogeneous would just be C1 cosine of x plus C2 times sine of x. All right, so now you're treating cosine of x as your u1, sine of x as your u2, and so the particular will be some function of x, I'm going to call it c1 of x, times cosine of x, plus some other function of x times sine of x. Now, and then I'll write it over here. Remember that we're going to take the derivative of c1 and multiply it times u1 plus the derivative of c2 and multiply it times u2 and set that equal to 0. And we're also going to do c1 prime times u1 prime plus c2 prime times u2 prime, and that's equal to f over a naught. So just my little side note for you to refer to. Where am I going to come up with these equations right now? Because this is true, this is the particular, as long as it satisfies both of these equations. All right, so here we have C1 prime of, right, it's of x, but whatever, and U1 is cosine of x, plus C2 prime times sine of x equals 0. And the second equation I've got is C1 prime times the derivative of cosine. Well, that's negative sine, so it's a negative sine of x. And then plus C2 prime times the derivative of sine, which is cosine. And we said that guy equal to f divided by the leading coefficient. Leading coefficient's 1, so it's just setting equal to f, which is secant of x. And now we want to solve this system. And what I notice is I've already got opposite signs here. And so I'm going to take the first equation, and if I multiply it by sine of x, and I take the second equation and multiply both sides by cosine of x, then what I'll have is these two first terms will be opposite in sign, but the exact same terms, and then when I add them together, they will cancel out. I did not leave myself enough room, so I'm going to come down here. So that means when I distribute this sign into all of these terms, that means I would have C1 prime sine of x times cosine of x plus C2 prime times sine, so sine squared, and sine times 0 is still 0. Multiplying cosine times the second equation will give me a negative C1 prime sine of x times cosine of x plus C2 prime cosine times cosine, so cosine squared. And then cosine times secant, they're reciprocal, so that's just 1. Nice. Very nice. All right, so let's add these two equations together. And bye-bye, ta-ta. And then these become C2 prime times the quantity sine squared plus cosine squared. and then 0 plus 1 is just 1. And of course, you know your Pythagorean identities. Of course, you know that sine squared plus cosine squared is not 0. Fail. Oh my Lord. It's 1. Of course, it's 1. And so you've got that C2 prime is just 1. Nice. Okay. So now let's plug that into either one, but the first equation is definitely the simpler one to plug it into, right? So I would have, so plug into first equation. So that way I can solve for C2 prime. So C1, or I'm sorry, I solve for C2 prime. I'm now going to solve for C1 prime times cosine of x plus a 1 times sine of x equals 0. Let's plug in the C2 into prime into there. And that means that you're going to subtract sine of x and divide by cosine of x, and that's what's going to give you C1 prime. Now, of course, you know that this is negative tangent of x. But in reality, when I go to integrate this, I'm actually going to leave it like this. Because when, do you remember, like when you have to integrate tangent, you'd have to rewrite it as sine over cosine anyway. So that's what we're going to do. We're going to integrate both of these guys to figure out what their functions are, C1 and C2. So C1 is some function of x, and we're going to get it by integrating negative sine of x over cosine of x dx. And hopefully you remember why we leave it like that instead of keeping it looking like tangent. And that's because, do you see that if you let u equal cosine of x, its derivative is sitting right there. So if you let u equal cosine of x, well then du is going to equal negative sine of x dx. And so you've got 1 over u du sitting right there. So this is 1 over u du, which of course we know the antiderivative of that is the natural log of the absolute value of u. And now don't forget to replace that u back. We let u be cosine of x, so that means it's the natural log of the absolute value of cosine of x. All right, then we're going to do the same thing with C2. C2 is some function of x, and we'll find it by integrating the derivative of C2, which we said was 1 with respect to x. And so that one is just x. And so your particular solution is C1 times, which we said was the natural log of the absolute value of the cosine of x, and then times u1, which was cosine of x, plus c2 of x, so x, times u2, which was sine of x. And so, and of course, I am not leaving that like that. I'm, of course, going to bring the cosine in front because, oof, yuck. All right, so your solution is homogeneous part, which we said was c1 cosine of x plus c2 sine of x was the homogeneous part, and then plus the particular part, which we said was this guy, but I'm going to throw that cosine of x in front of the natural log of x, and then plus x times sine of x. And of course, that's the particular part. There you go. There's your solution. Da, da, da. All right. So a variation on this is, here's a variation, is if you're solving a second order, and it doesn't matter if it's homogeneous or non-homogeneous. I'm adding Linear differential equation given one solution, given one of the homogeneous solutions to L operating on y equals 0. So if we're solving a second order one, but we've been given one of them, then if y1 is one homogeneous solution that we've been given to a second order linear differential equation, then what you're going to do is you're going to let y equal v times y1. You're going to let y equals v times, remember, y1 is the one homogeneous solution they gave you, to solve either the homogeneous or the non-homogeneous. Homogeneous DE if it's L, y equals 0, or the non-homogeneous if it was Ly equals F. All right, so let's do an example doing this. So given the differential equation, xy double prime minus 2y prime plus the quantity 2 minus x times y equals 0. The first thing we're going to do is we're going to verify that y equals e to the x is a solution to this homogeneous. Remember, it's equal to 0. It's homogeneous differential equation. Okay. So what I need to do is I've got y, I need to find y double prime and y prime, and then plug them in and verify. So if y is equal to e to the x, y prime is e to the x, and y double prime is, gotta love e to the x. It's my favorite function to differentiate. I'm sure it's yours as well. Okay, so plugging it into this equation here, x y double prime minus 2y prime plus 2 minus x times y equals 0. So I would have an x times e to the x minus 2 times e to the x plus 2 minus x times e to the x. Is that equal to 0? Well, let's see. Got an x e to the x minus 2 e to the x. Distributing the e to the x to the 2 and to the negative x. And that is definitely equal to 0. Bye-bye. Bye-bye. See you later. Okay, so then part B is going to be, now let's find the general solution. So here's where I've got one of them, right? So I'm going to let y equal v times y1. Well, this was my y1, right? That's your y1 that you're going to plug in there. So it's letting y equal v, and then v is what we're going to end up solving for, right? Times e to the x. Okay, so then what you're going to do is, if you've got y, right, we need y prime and y double prime in order to plug these guys in. So first derivative would be, keep in mind, v is some function of x, right? So we do have product rule happening here. So it would be the derivative of v with respect to x, right? So, but I'm just going to abbreviate it as v prime times the second guy plus v times the derivative of e to the x with respect to x, which is e to the x. So just keep in mind, I should probably write that. V is a function of dx. So v prime truly means dv dx. You're taking the derivative of v, but with respect to x. So hopefully that makes sense of why it's definitely product rule there, because you've got two different functions of x here. All right, then second derivative would be, I'm going to take the derivative of this guy. All right, so then that means this is, again, product rule, right? Derivative of the first would be v double prime times the second plus the first times the derivative of the second. So that's the derivative of the first term. Do the same thing with this guy, and, well, you know, the derivative of this guy is what we did when we took the derivative of this one. So it's just y prime. So it's another v prime e to the x plus v times e to the x. Went faster because we already found c1. Well, these two guys are like terms, right? So you can simplify that. And that would be v double prime times e to the x plus 2v prime e to the x plus v times e to the x. All right, so now we're going to substitute these into our equation. Substitute into your differential equation, right? Remember, the equation was x, y double prime minus 2y prime. I just want to make sure you see where I'm plugging this in. Okay, so now, but I'm going to be plugging in this guy into y prime. I'm going to be plugging this guy into y, I'm sorry, this guy into y double prime, this guy into y prime, and then this one into y, which you don't see on the screen. There we go. Okay, so I've got an x times the quantity v double prime e to the x plus 2v prime e to the x plus v times e to the x. Yeah. Okay, and then minus a 2 times y prime v prime e to the x plus v times e to the x, and then plus the quantity 2 minus x times y, which was just v times e to the x, and set that equal 0. And our goal is to solve for v. That's our goal. And so what I notice, first of all, is that there's an e to the x in common to every term. So I'm going to take this whole thing, both sides of the equation, and I'm going to divide it by e to the x. Yeah. And so then I would be left with an x v double prime here, plus 2v prime times x. Don't forget to distribute. So let me, I want my x in front of my v's. So times 2 times x times v prime, and then plus x times v. That was this guy. I got rid of all the e to the x's, but distributed the x. Distribute a negative 2 into both of these, but I'm also dividing by e to the x, so I get rid of those. So I've got a minus 2v prime and a minus 2v. And then same thing here, divided by e to the x here, so got rid of that, but then distribute a 2 into there, so a plus 2v, and distribute a negative x into there, so a negative xv, and then 0 divided by e to the x is still 0. All right. We can simplify this. Let's see. Well, some things cancel. X times v minus x times v, negative 2v plus 2v. And that looks to be about it. So I am now left with x v double prime plus 2x v prime minus 2v prime equals 0. All right, so I can, these two guys are the same term, so I could put them together. Yeah, let's do that. This is xv double prime plus a 2 times an x minus 1 times v prime. Yeah, I could have factored out a 2x minus 2, but, and that would have worked too. Whatever, doesn't matter. I just noticed there was also a 2 in common, so factored out the 2 also. All right, so here is where I'm going to do another substitution of a variable because, we haven't done it enough yet. I'm going to let u equal v prime. That means u prime will equal v double prime. And then this becomes x times u prime plus 2 times the quantity x minus 1 times u equals 0. And why did I do that? Because I just made it separable. Nice, right? So keep in mind, u prime is a function of x, right? So it's the derivative of u, but with respect to x. So I'm going to rewrite that so that it's more obvious. So this is x times du dx, and then I'm going to bring this over to the other side, is equal to negative 2 times minus 1 times u. And maybe now it's more obvious that it's separable, right? I'm going to divide by x, multiply by dx, divide by u. And I'm getting all of my x's over on the right. I'm getting all my u's on the left. So it would be a 1 over u du would be equal to negative 2 times x minus 1 over x and then dx. No? Well, I guess I really shouldn't have factored out the 2 because do you see that? Well, I guess it doesn't matter. You can still see it. That this becomes a negative 2x divided by x, which is just a negative 2, and then a plus 2 over x. Yeah, dx. That makes sense. All right, so now when I choose to integrate both sides, 1 over u du is equal to the integral of negative 2 plus 2x dx. Left-hand side is the natural log of the absolute value of u. And right-hand side, because I separated it like this, it's much easier to see that this is a negative 2x plus 2 times the natural log of the absolute value of x, and then plus c. All right, we want to solve for u because then we're going to solve for v, and then we'll solve for more. But anyway, okay. So solving for u means you would take e to the power on both sides, right? So e to the natural log of absolute value of u will leave you with the absolute value of u. And then this is e to the negative 2x plus 2 times the natural log of absolute value of x plus c. And then do you remember we did ones like this, right? Where same base, keep the base, add the exponent. So that means this right-hand side is equivalent to e to the, I'll come down here. I don't want to make it messy. Okay, this is equivalent to e to the negative 2x times e to the 2 times the natural log of the absolute value of x times e to the c. Remember all of that? And then how do we drop off the absolute value symbol? By putting plus or minus and keeping in mind that e to the c is a constant. So I can drop off the absolute value as long as I'm writing, okay, this is plus or minus, and then I'll put it on the e to the c, you know, and then times, we've got, well, you know I'm going to put this in front, but I won't for a minute. Okay, so times e to the negative 2x, and then times, do you remember this, is you can take that 2 and put it on the x, and then e to the natural log undoes itself. So this is equivalent to x squared. Yeah. All right, then, do you remember the little trick of I'm now going to go, this is a constant, so I'm going to choose some other letter. I'm going to let, how about if we let C, do I want C1? How about if I let K, just for giggles, let K equal the plus or minus e to the C. Yeah? Okay, so then that means that my U is K times, and it's just typical to put the algebraic part first. So times x squared times e to the negative 2x. Yeah. But remember u, we had done a substitution of variables. U is v prime. Yeah. And so then that means that I've got v will be the integral, the antiderivative of kx squared e to the negative 2x dx. Okay. Phew, we're not done yet. We got to integrate this. I see, remember k is truly a constant, right? I see a function times another function. You're trying to integrate it. This would be integration by parts. But because one of them's algebraic and the other one is a loopy one that just keeps on going around, you can definitely do tabular, which is much easier. So I'm going to do it tabular, where my algebraic function is what's going to be my f of x. So kx squared, derivative of that would be 2kx, derivative of that would be 2k, derivative of that would be 0. And then e to the negative 2x is going to be my g of x. And then remember, we do antiderivatives on the g of x. So you're going to undo the chain rule. So it would be, if you were taking the derivative, it would be times negative 2, but we need to undo that. So it's a negative 1/2 e to the negative 2x multiplied times another negative 1/2, so a positive 1/4 times e to the negative 2x. And then times another negative 1/2, so a negative 1/8 e to the negative 2x. And you remember we go plus, minus, plus. So that's you certainly could do integration by parts using, what would you remember we called it, ultraviolet voodoo, the uv minus the integral of v du. But tabular is much faster. All right, so what does that mean? I'm going to come over here because I took up room over there. Your v is kx squared times negative 1/2 e to the negative 2x. So I'm going to write it as negative 1/2 kx squared e to the negative 2x. Yeah. And then minus 2kx times 1/4. So that's a minus 1/2 kx times e to the negative 2x. And then the last one would be a positive 2k times negative 1/8. So that's a negative 1/4 k times e to the negative 2x. And then we do have some other, this was a indefinite integral, so plus some other constant. Let's call it c for right now. Yeah. All right. So let's clean this up a bit. I could factor out the e to the 2x out of all of these guys. So this is, if I factor out, I do that. Oh, I can also, okay, so they all have an e to the 2x in common. I'm sorry, an e to the negative 2x in common. They also all have a k in common. They also all have between -1/4 and -1/2. -1/4 is the smaller one. So I'm going to go ahead and I'm going to factor out a -1/4 k e to the negative 2x. And what am I left with when that happens? Well, that would be a 2x squared from the first term, right? Since 2 times -1/4 will give you that guy. And then another plus 2x. And then here, 1/2 k, there you go, plus 1. And then plus that c value. Yeah. Okay. Now, we still need to solve for y, not just v, right? Because v is not our final answer. But I'm going to clean this up even more. And I'm going to call, that's a constant. I'm going to let this be C1. Just because that's what we do. And then I'm going to call this guy B, C2. Yeah. All right, so that means my V is equal to C1 e to the negative 2x times the quantity 2x squared plus 2x plus 1 plus some other constant. Now, that's just what's typical. Instead of using two different letters with these, we use C1 and C2 to represent that they're constants, but they're different constants. Okay, so that's V. That's not our final answer because we need to solve for y. And if you remember, y was equal to V times e to the x. Yeah? All right, so that means that y must equal, this whole thing is V, and then times e to the x. So it's the C1 e to the negative 2x times the quantity 2x squared plus 2x plus 1. And then plus C2. That's your V. And then we're going to multiply this whole thing times e to the x. All right. Keep in mind that there's only two terms in this, right? This is your first term, and then plus C2 is the second term. So you're going to distribute the e to the x to the C2 and to that guy. But when you distribute it to this guy, you're just going to multiply it times e to the negative 2x. And so, final answer. And then we're done. You ready? When you multiply e to the x times e to the negative 2x, you're left with e to the negative x. So you've got C1 e to the negative x times this quadratic, and then plus C2 times e to the x. There you go. I know, crazy, right? I understand. All right. I hope you all are having a fabulous day. You can see my screen, so you can see it messing with me.